Now let's say hourglassing and try to understand how hourglassing occurs in first order reduced integration hex elements with hands-on workshop. So we will take the previous same model of pure bending moment of cantilever beam, which we have taken for shear locking. So I will save the model in hourglass folder. Okay, so I will say C3D8R. Okay, so we are going to the reduced integration element. So let me delete all this analysis. So we will start with one element along the thickness. Okay, so let me change this to, we know our dimensions are 16 by 10 mm. I will take one element along width and thickness and mesh it. Okay. Here we can go into this FE model tree where solid part is there. We can just double click and open it and change the element type. Okay. So this is full integration. I will change it to reduced integration R. Okay. So that's it. Remaining everything gets updated automatically. So let me create analysis C3D8R, one element along thickness. Let's see the results. So we see the von Mises stress is 0. Okay. Similarly, the stresses components bending stresses S11 is also 0. Shear stresses are supposed to 0, so that is fine. But we are also seeing bending stresses as 0. Okay. So these are nodal outputs. Let's see integration outputs. Okay. They should also be 0. Okay. So we see it is everywhere. It is 0 stresses, 0 bending stresses. So this is hourglassing. Though if you see the initial, there is a deformation. The deformation has happened, and under this rotation by boundary condition, okay, and we see the displacement of 8.74 mm. But we were uh, supposed to get some bending stresses, and we have seen that our theoretical bending stress is 612 megapascal. Okay, so though the deformation is happening, the structure doesn't have any strain energy or stresses. Okay, so these are zero energy mode, which is called hourglassing. So as we discussed that we can add more element and we can overcome the hourglassing issue. So let's do that. I will add two elements now along the depth and width of the cross section. Let me run this analysis with two element in thickness. Let's see results. Okay, the displacement is okay. That is my boundary condition. Okay, the equivalent rotation I have applied. The stresses are now 300 megapascal. So from 0 it is 300. So let's see bending stresses. Okay, which are 312 minus 312. Okay, these are nodal outputs. Let's see integration outputs. That is also 312 megapascal. Okay. So I am getting bending stresses, but it is not close to my theoretical bending stress, that is 612 megapascal. Okay. And shear stresses are 0. Okay. So this is a good that we don't get any shear locking in with reduced integration elements. Now let's add few more elements. We will now add four elements along thickness. and rerun analysis. So bending stresses are now 477 megapascal and shear are almost zero. Okay, these are nodal. We can check integration shear stresses. Okay, that is almost zero. Okay, and S11 axial stress or normal stress components. So I am getting around 460. Okay, 476 or 460. So these four elements for this particular case, it is not sufficient. Okay, because I my target is 612 megapascal. So I will add few more elements, 8. Okay, this should be 2 mm. With 8 elements along thickness. Okay. So bending stresses are 580 megapascal, very close to theoretical values. And at integration points, we are getting almost 536 megapascal. Okay, or 579, the highest. Okay. So we can check the that file output. Okay, this is just there is a limitation in user interface. It will only report 100 columns. Okay, in that file you will see complete report. But what I'm trying to say, we are moving close to the theoretical output. Okay, by refining element along the thickness and by removing or eliminating hourglassing. And as we know, the theoretical stress 612 megapascal is on the surface, whereas integration points are below surface. So we can never get 612 megapascal. The concept of hourglassing is clear, and what we should do to eliminate hourglassing. Now let's come back to these slides. So let's discuss the summary of bending dominated problems. As we have discussed, the preferred element types are C3D8R, okay, when there is a bending, not C3D8. Okay. If we want to use full integration elements, we can use C3D8I. I stands for incompatible mode elements. Okay. So these incompatible mode are added additionally to elements. Okay, so it adds additional degree of freedom in the element. This is to prevent the parasitic shear stresses coming from shear locking. Okay, and that way, if we want to use first order hex elements full integration, then use I element, okay, incompatible mode element. Otherwise, simply go for reduced integration elements. The simple rule is that use minimum 4 to 8 elements along the thickness of structure in bending. Now, in reality, there is not always pure bending in any structure. Okay, when we work with real structures, okay, there is a bending as we have shown earlier. It will never be a pure bending. So the structure is subjected to a combination of deformation modes, bending plus shear, torsion, all these things. So you will see in your real FEA problems, you will see shear stresses. So don't get panic when we see shear stresses. It is supposed to be there because it is not always pure bending deformation in real structures, at least in mechanical structures. Okay. So the simple key takeaway is that use this element type or C3D8I element. Okay. Other thing is that these C3D8R elements are computationally very inexpensive. Okay, they run very fast because it has only one element. If we talk about hex 3D hex element, okay, uh, C3D8, it has 8 integration points, okay, internal to the element, whereas C3D8R has only one integration point, that is at the center of the hex element. So it is almost uh, 8 times inexpensive or cheaper than C3D8 elements when coming to the computation of stiffness matrix. So we know the stiffness matrix computation. Okay, each term is contributed by integration points, right? Please revisit the previous module where we have discussed this in detail. Okay, so the stiffness matrix computation becomes very fast when we go with C3D8R element. Even if we use 8 elements, okay, it is way cheaper than C3D8 elements. Okay. So though the degrees of freedom will remain same, okay, uh, or number of equations remain same, okay, the K matrix, if it is n by n, where n is degree of freedom in the FEA model, this will remain same, but the stiffness matrix computation, okay, will be faster. Okay. Similarly, once we get the solution displacements after doing our FE analysis, as we know the first, the we also need to compute other derived quantities like strains and stresses. So strains and stresses are also computed at integration points, and we need to compute this at only one integration point in case of C3D8R. So that way, this is what I am trying to explain. These C3D8R elements are computationally very efficient.